Walk through any major airport terminal and you will see two distinct states of passenger behavior: the fast-moving flow of people navigating toward their gates and the sudden stationary stock of passengers who come to a halt to wait for boarding. For decades, the commercial aviation industry has operated on a straightforward assumption regarding that waiting period. When flights are delayed, passenger dwell time increases. That extra time trapped in the terminal should automatically drive higher food, beverage, and retail sales. To test this assumption, airport analysts typically use a simple binary comparison. They take the total terminal revenue on dates with flight delays and compare it to the total revenue on dates without delays. This scatterplot maps exactly that approach, applied to thousands of flights across domestic Terminal 1. The x-axis shows mean sales during normal operations, and the y-axis shows sales during delayed operations. If delays caused a massive surge in spending, these points would sit high above the baseline. Instead, they closely hug the 1-to-1 ratio. When we convert those points into side-by-side box plots, the distributions are nearly identical. Across the entire terminal, delayed flights produced a median sales lift of only 2.4%. Looking at a 2.4% bump, executives often conclude that operational delays have little meaningful impact on commercial performance and therefore require no specific retail strategy. But total revenue is a flawed metric. Sweeping terminal-wide averages dilute localized data. By blending every store and every gate together, the aggregate numbers hide the actual economic reality of operational disruptions. To see the actual effect of a delay, we have to look past the terminal average and examine a specific localized environment. Consider the case of Tiffin Express, a food and beverage outlet located at the East Bus Gate. Look at this operational data table for Tiffin Express during a period of heavily delayed flights. The top row highlights passenger volume. During the delay exposure, the physical area surrounding the store experienced a 42% surge in captive foot traffic. The baseline expectation in retail is that a 42% increase in foot traffic should yield a proportionate, or at least positive, increase in total revenue. Instead, the store's actual sales collapsed by 32%. How does an airport concession receive a massive influx of captive traffic, yet simultaneously lose a third of its revenue? This paradox proves that revenue alone is a dangerous lagging indicator. To diagnose what happens during a disruption, operators must decompose total sales to understand why a store is failing operationally despite a captive crowd. This equation is the four-lever decomposition matrix. It breaks total hourly sales down into passenger volume, penetration rate, and average transaction value, allowing us to pinpoint the exact commercial bottleneck. Penetration rate measures the specific percentage of available passengers who actually complete a transaction. It is the purest measure of a store's ability to convert footfall into customers. We then calculate sales per passenger, or SPP. This metric combines penetration and average transaction value to reveal the overall commercial efficiency of the operation. Applying these metrics to Tiffin Express solves the paradox. Despite a 42, there are pure commercial winners, traffic-driven responders, and missed opportunities like Tiffin Express. Without tracking data, we have to pivot our analytical approach. Instead of attempting to trace the flow of individuals through the terminal, we model the spatial temporal stock, the actual accumulation of passengers in a specific zone. We do this by combining the airport operational database flight logs directly with electronic point-of-sale data at a highly localized level. Look at this terminal map. By mapping a specific food and beverage outlet exclusively to its nearest boarding gates, we create a spatial catchment zone. We link the store to its primary gate, plus the immediate adjacent gates on the same level. Spatial catchments allow operators to accurately measure the unique operational environment immediately outside a specific storefront. We get localized passenger volume and delay exposure without needing invasive tracking technology. Once the zones are established, we have to measure the disruption accurately. Using a simple binary yes or no flag to mark a flight as delayed is flawed. This diagram shows two vastly different realities. On the left, a minor 15-minute delay for a 40-passenger regional flight. On the right, a severe 2-hour delay for a 250-passenger wide-body. A binary system places a generic delay tag on both, treating them identically. To replace that binary tag, we use a continuous variable, the Commercial Opportunity Index. We multiply delayed passengers in the catchment zone by their departure delay minutes. The 15-minute delay generates a score of 600. The 2-hour delay yields 30,000. Applied to a store-by-hour panel, this metric scales precisely with the severity of the operational disruption happening outside the doors. The Commercial Opportunity Index transforms ambiguous flight data into a weighted measurement of local potential. It aligns the data structure with the actual business opportunity. There is one final methodological error in standard airport analytics that must be corrected. Models typically assume that passengers react to a disruption strictly during the scheduled departure hour of the delayed flight. In reality, airlines know about maintenance, crew duty issues, or late inbound aircraft well in advance. They typically alert passengers to delays 1 to 3 hours early via mobile apps and terminal displays. When travelers receive an early notification, their discretionary dwell time shifts. They secure food or retail purchases long before they ever approach the gate for their original scheduled departure hour. To capture this shifted behavior, we deploy an event study window. We test multiple relative time windows surrounding the delayed flight to locate the actual behavioral response. This timeline plots the Commercial Opportunity Index against retail KPIs. We examine 2 hours before the scheduled departure, 1 hour before, the departure hour itself, and 1 hour after. The data locates the peak commercial signal occurring well before scheduled departure. Finding the strongest empirical signal in a relative window is essential. If you guess the exposure hour based solely on flight schedules, you will misattribute the sales and completely miss the true commercial impact of the delay. By moving away from aggregate terminal revenue and scheduled departure hours, we can finally measure the localized effects of operational disruption. This flowchart tracks the unified workflow. First, we integrate operational flight logs and POS transactions into distinct spatial catchments. Second, we calculate the disruption magnitude using the Commercial Opportunity Index across an event study window. Finally, we evaluate outcomes through the 4-lever decomposition matrix. This entire process operates without the need for expensive passenger tracking infrastructure, utilizing only routinely collected databases. Abandoning the trap of top-line sales empowers airport commercial teams to precisely diagnose retail failures. They can finally see who is merely surviving the footfall, who is buckling under the pressure, and exactly how to convert operational disruptions into a data-driven commercial strategy.